This is Cosmographia, the Randall Carlson podcast. And welcome back, ladies and gentlemen, to Kosmographia podcast. It is a beautiful fall evening here on the Edwards Plateau in South Central Texas. And how's it going out there where you guys are? Randall, Brad?
Beautiful weather in Georgia. Nice. It's cooled off a bit, although we need some rain. If you got any extra rain, send it our way.
Very, very dry up here, but yeah, nice fall day today.
Yes, absolutely. So we just got back from a long trip in the northeast, and we are excited to be back doing this podcast with you guys.
Yep. Barely scratching the surface.
That's right.
Everywhere high and low.
Well, tell us a little bit about your what you guys were looking for up there, and if you found anything of interest.
Yeah. So we had visited this area in Vermont years ago. And it's basically just in a national forest. There's an area with a lot of rock cairns that are sort of anomalous. There's a lot of rock piles and rock walls all around the state from old farmlands and stuff. But this one is quite strange. The piles of rock are highly concentrated compared to everywhere else. And in a very small area, there's about 150 mounds. And they're very well stacked. I mean,
they're not piles.
They were made by stonemasons.
Yeah.
They're not hewn, but they're raw material, but they're beautifully stacked and
so they're not random piles.
Right.
No.
So they're deliberate. Somebody stacked them in a certain way, or
yes. That's right.
And it looks, the workmanship is regular. It's the same across many of these piles. It just looks like the same person did this work or the same individuals that were trained to do it.
So what time frame were these things created?
It's controversial.
Yeah.
So of course.
The standard model is saying that they are colonial, basically, that they were put there by homesteading farmers, colonial farmers, right?
For what purpose?
Right.
To clear the land of the rocks.
Right.
Okay.
But they're so concentrated that it's almost, you get the opposite. You're crowding the land with the rocks.
Yeah.
And also the land is, they've actually done some soil samples out there and found that
a lot of
much
these areas
of it has not been tilled.
Right. It was never farmed in the normal sense. So, and so the other thing is that there are interesting choices of what rocks go where, right? So there's a bunch of beautiful erratic quartz in the area, and sometimes they're enormous, giant blocks of quartz that were brought there by glacial action. And oftentimes the quartz in the particular mounds will be concentrated to one side or to one corner or to the top upper corner part, or or even when there's boulders that have quartz inclusions, they will have those specifically to the outside so that they're visible. So it's all very interesting. And the other thing that we went to look at was,
and I'm sure you got pictures of all of this.
We did. Yes, we did. And we went to look at sites called Calendar 1 and 2, which are actual stone chambers. So they're subterranean chambers. So when you find them, it's just a hill. It looks like a hobbit house, but the face of it is made out of dry laid stacked raw stone, and there's just a square opening into the ground. And you walk through a very tight passageway, and then it opens up in there into a small interior chamber that has one of them. The stone chamber number 2 had I don't know what it was, a chimney hole or something in the back.
Window. Rectangular
window, and they're aimed at the equinoxes or solstice that the entrances are, so that on that day, if the forest were clear, which is not the case now, all these woods have grown up, but if it was clear, the sun would come through and down the passageway and light up the back of the chamber on that day. So,
well, that doesn't sound like something that would be done by colonists. I mean,
right.
No.
or farmers, because I mean, to my knowledge, they didn't have any motive for doing that, and
Exactly.
wasn't standard practice for them. I mean, that's not to say that some of them may have engaged in such things, particularly if they were, members of a certain order or something. But it doesn't sound like. I mean, this sounds more consistent with, a lot of the old Neolithic stuff, and even coming
That's
down, So yeah, at some point maybe we should do a thing on the, on the mound culture.
Yes.
Yeah, absolutely.
That would be great.
Mhm.
Is that something Scott Walters looked at up there? Do you know? You guys
That
talked
I
to
don't
him?
know. I know Jim Vieira has looked at a lot of these places. So he's done a whole. He's actually got a TEDx talk on the stone chambers of New England. So he was the first. He was the one that I actually contacted him the first time we were up there 6 years ago, and asked him, "Hey, where's something near where we are to go check it out?" And he pointed us to the area that has all the cairns, and then that led to us hearing about these other sites, and then we were able to actually find them this trip, which was fantastic. So
yeah, and we got in touch with some people. Actually, I've got the contact information for a scientist woman who went out with a team and mapped all of the cairns in this site. And then our contact who gave us her contact information sent us a paper that she wrote about that site. And it is fascinating.
Really
and there's
good.
a lot of attachments that I don't have. He just gave me the text, but there's maps and all this other stuff. So we're going to contact her and see if we can get some more information from her, and then possibly see if she'll come on the podcast, our podcast.
Great. What did so there was supplementary information then that you guys couldn't access? Is that, and where
Right.
did she publish in a journal, or where the paper was it published, or was it?
I don't think I'm not sure. I can look that up.
it may have been submitted to the National Park Service because
Yeah,
it's on their land.
I don't think it's been published in like a journal.
She did the
Fair.
survey at the behest of the Forestry
I see.
Service. So
Well, then they would probably have a copy of the report, but
Right,
you could probably get it directly from her.
right. And I think that the idea for them doing this survey and everything was because the Park Service is trying to find out what are we protecting here?
Yeah.
Yeah.
Are
Sure.
these colonial piles of rock that aren't really anything, or are these actually much more ancient and therefore much more fragile and something that we need to be very careful with?
Well,
So,
clearly, if they've got unambiguous astronomical alignments in them, they need to be preserved.
yes, absolutely.
So that's
what size are they?
Well,
cairns?
some of the cairns they're all sizes. Some of them are literally, 2 or 3 feet in diameter and maybe a foot tall.
Mhm.
There's some erratics that just you could see a couple of layers of stone, like maybe they've been knocked off, but just a few. And then there's some that are
Enormous.
bigger than a house.
Yeah.
They're 10 feet high, and I mean just
Right. Okay.
massive.
Yeah, and some
Works.
of the stones that are in the walls are gigantic. So
Mhm.
and obviously can't tell really how big they are because all you can see is one face, just the wall, just the one on the facing wall. You don't know how big it is going back into the thing, but there are some enormous stones, truly enormous stones in some of these constructions.
I think the longest or the largest on the field is about 14 meters long.
Really?
Okay.
Yeah.
That's large.
Yes. So the other thing that was cool that we got to do is there is a Serpentine Quarry in the area.
Hmm.
And it's actually right next to, we went up there to see family. So our uncle has a house there, and right next door to his property is this quarry, and it's been in operation since the late 1800s.
Hmm.
So the current owner of the quarry is really cool and is good friends with my uncle. So my uncle was able to arrange for us to have a tour of this quarry. So we got to go in there and talk to the guy about just moving enormous blocks of stone, cutting and moving huge blocks of stone from quarries, and what he thought about some of the ancient constructions around the world and how they may have done their cutting and lifting of stones, and it was a lot of fun. So
I'm sure it was.
Yeah. And of course, it was serpentine.
Mm-hmm.
Yeah,
of
great
course,
for us, right?
Yeah.
Snake nose, turret.
Yeah, I was noting that little connection there.
Yeah.
So
what did you guys do last week?
Yeah.
Oh, I'm just in the midst of, I told you guys we've got this restaurant project that we're about to start. Well, actually, it's taken about a year to put the whole thing together, get the permits, get everything set up. I mean, when you build a house, there's a lot less than bureaucratic red tape that you have to deal with, say, as compared to a restaurant, which first time we built a restaurant, so there was a huge learning curve for me. But
like a commercial building, you mean?
Yeah, and the building is there, but basically we're stripping the building down simply to the block walls and the roof, and then we're rebuilding everything inside and outside. But yeah, so there's been a lot to it, and so the permits just finally got released the week before last, so about a week and a half ago, not quite 2 weeks ago, somewhere in there, where they finally released the permit. After jumping through hoops for a year and thinking we had everything in place, then finding out we needed more things, and then thinking, okay, now we got it, and then we find out we need more things. And so finally got the permit. So we've got that. And then I've got 3 projects in the pipeline, pretty good sized projects that will keep the team busy for about a year.
All right.
And the cool thing about that is all 4 of these projects now are archetype builder Randall designs. They're all very close to where I live, so they're going to be easy to manage. And actually, since I don't really do much of the day-to-day managing, my brother does that. That's going to be great for me.
That's
so
some free time,
more podcasting,
right? More podcasting and
book writing,
podcasting, field trips, whatever. Yeah, and yeah. So these are maybe sometime we'll devote a little session of one of the podcasts to I'll show some of the work that we've done over the years.
Yes.
Some of the more interesting projects that we've done.
We're going to start doing 2 a week.
Brad's serious.
Well, we easily could. I mean, if we had the time, it's not like we don't have the material.
That's right.
Well, one to keep on the track of all your programs, and then one to interact with daily news and scientific reports and publish papers and interview other people to have guests on. And I mean, there's just
yes, and every week there's interesting stuff that would be worth talking about.
Yes,
every week, new things to talk about. And I've got we need to get George Howard on here.
We do.
Absolutely.
Have a rousing discussion about the Younger Dryas boundary, and
I'm going to call him this weekend.
That would be great. Yeah. He'd be fun to have on. And
good. And maybe we could get what's the other guy? Alan West on here. That would be great. I don't know.
That would be,
if he's ever done an interview, or even Richard Firestone. Get the Firestone guy on here. Let's talk to him about.
We can build up to that.
Yeah.
Oh yeah.
We got the right network.
Talk to him about burning rocks from
That's
space.
Right. Giant burning rocks from space. Tell us about that, Firestone.
Right.
Yeah. When did you change your name?
Aptronyms. Randall, have you ever looked at aptronyms? I'm fascinated by this. Right names. It's just so strange.
Oh yeah, I have a list of those that I've made a couple of years ago where I was noticing the names, the association between the name and the.
Yes,
and they'll come to me in a second, but I don't remember them right offhand.
The guys who came up with the hypothesis for a comet impact in the West is Firestone and West.
Firestone and West.
Well, yeah, right.
Genius.
Yeah.
How did that happen? And then
Life's mission from the beginning.
One of the first guys who was looking at the I think this was the Carolina Bays related, but he was looking at possible impacts in the ice sheet and how that would throw what would happen if it throw, and his name was Melton.
Oh yeah.
And I'm just like, how is this happening?
Melton and Shriver?
Yeah.
Melton and Shriver. Yeah, they wrote one of the early series of papers, or I think it was Melton and Shriver that wrote the first paper speculating the Carolina Bays were produced by extraterrestrial impact of some kind. I'm
Yeah.
quite sure that was the first
Melton.
paper. Melton, yeah, Melton. Okay.
I collect aptronyms too, so I'm glad that you do that also. It fascinates me.
What's that word?
Aptronyms.
Aptronyms.
Yes, names that are apt.
Oh, aptronyms. Perfect.
That's what they're called. Hey, I looked it up.
All right.
Aptronyms.
My last name's Young, and I'm sticking to it.
Good deal.
Well, my last name is Carlson, and it means I'm son of Carl.
All right, there you go.
But I'm not really. I'm the grandson of Carl. See, the Swedes finally figured out that wasn't going to work anymore.
Yeah, it seems to. Yeah, Carlson.
Yeah, right. Well, if my grandfather was Ole, then his father was Carl, so then I would be the son of Carl, the son of Ole.
Yes.
See, so.
Man, you should get at least 4 or 5 of the names going back so that you can be like, I'm Randall Carlson, son of.
I can come in here with the trumpet and Kyle can announce all of your names like the bard, right?
Well, okay, so I'll get to work on that.
All right, good.
Yeah. No, I've actually, somebody, not to get off on this digression, but, my father had 3 sons by my mother, a couple of sons by another mother, but 3 sons by my mother, which are my 2 brothers, right? And so my father, I'm trying to remember how this went. So he has a cousin in Sweden that he's never met. And somebody that we know, like this is 20 years ago, maybe longer, 30 years ago, went over to Sweden and met this cousin of my father who has 3 sons the same age as me and my brothers. I thought that was kind of interesting.
Yeah, that is interesting.
Yeah. So I
it's like twins separated at birth live very parallel lives, same car.
Yeah,
same
it was
job,
kind of like
same,
one of these parallel universe things.
Yeah.
My dad's cousin.
Same. They marry a woman that has the same first name. Yeah, it's
right.
Resonance.
Yeah, maybe that was it. Yeah. So he had these 3 sons, and the guy said that my dad's cousin actually even looked sort of like my dad, and then so he had these 3 sons that were all the same ages as me and my 2 younger brothers. So I don't know what that's all about. There are coincidences, right?
There are, yeah.
There are things that are just coincidental, right?
Sure, yeah.
There are things that we can say, okay, that has no meaning, right?
Yeah.
And we don't. I don't need to bother about that anymore because that one is actually a bona fide coincidence.
Nah, that's harmonies. That's what it sounds like.
Energetics, resonance somehow.
Yeah, it's resonance.
Well, speaking of coincidences, we should probably talk about the things we have been talking about because there's a little bit more we want to get into. Because it seems like a lot of people are interested in this question of the Recatch structure.
That's right.
Right. So my first encounter with that must have been, guessing late 70s or early 80s. There was actually a paper published in the late 60s where a French geologist thought he had discovered Coesite. Have you ever heard of Coesite?
No.
Okay, Kyle, get to work, my friend. C-O-E-S-I-T-E, Coesite. I think you'll find something like that. It's a high-pressure polymorph of silica. Okay. I don't remember exactly the pressures that are required to produce it, but it's considerable. I'm sure you'll find it right there.
Coesite is a form of silicon dioxide.
Okay.
That is very high pressure and moderately high temperature are applied to quartz.
Yep. Okay, and where do you get the kinds of pressures and temperatures that would be necessary to produce Coesite?
Under the earth?
Mantle?
No.
Impact.
Yes, impact. So it's one of the principal proxies for an impact event.
Oh, okay.
Coesite. Then, in fact, there's another one I think that's even more high pressure called stishovite. Stishovite is not relevant immediately to our discussion tonight, but when I became obsessively interested in impact cratering in the 70s and the 80s, I think is the first time I heard of the Recatch structure. And because at that time it was I think it was actually discovered during the Gemini program in the mid 60s. The Gemini astronauts were the first to photograph it. And there was a paper published in 68 or 69 where this French geologist believed he had discovered coesite at the structure. And if he did discover coesite, that would be strong evidence that it was produced by an impact. However, then other studies came along, and let's see here. I'll do a screen share in a second here. And the subsequent, here we go. Okay, so it
says that it is known to require a pressure of 300,000 pounds per square inch for its formation.
For coesite.
Yes.
Yeah. Wow, pounds. So there's not too many places in nature where you get those kind of pressures, except impacts. Pounds per square inch. Okay, let's see, get oriented to my screen again here. Yeah, here we go.
There we go.
So this came out in 1969, Coesite from the Richat Dome, Mauritania, a misidentification. The shattered sandstone from Recatch reported to contain coesite is a tectonic breccia and probably represents a shear zone developed during structural doming. We'll come back to that. An optical and X-ray examination of concentrates from this breccia demonstrated that the supposed X-ray reflections of coesite are actually due to barite introduced into the permeable crushed zone by groundwater. So subsequent studies seemed to disprove that it was actually coesite. And so the Recatch structure got kind of consigned to impact crater wannabes, but never confirmed, right? And so the scientific opinion now, again, it's controversial. I think you'll see, though, that this was one of the more interesting and recent studies done that I have accessed. The multi-analytical characterization of silica-rich megabreccias from the proposed natural area of Recatch. While you're at it, Kyle, you could look up the word breccia,
okay,
and share with the listeners what actually breccia is. Breccia is a type of rock composed of fragments of other rocks that have been broken, right, and usually cemented together by a mineralized matrix. But so breccia would be something that you would find associated with a lot of impact events, because an impact event is going to shatter rock, and it's going to create big old piles and masses of broken rock that can then later become cemented together, forming a subsequent type of metamorphic rock, which would be breccia.
Okay, so it says a rock composed of sharp-angled fragments embedded in a fine-grained matrix. In geology, a conglomerate in which the fragments, instead of being rounded or water-worn, are angular.
Yeah, broken.
But that's not the same as Shatter Cone. That's a different thing.
No, that's not the same as Shatter Cone. Okay. Shatter Cone is specifically to basically quartzite-based rocks or limestone, really more prevalently limestone. And the pressure wave moving through the limestone creates a very characteristic type of texture in the rock. Primarily, carbonate rocks, limestone and dolomite are the two. You can get some shatter coning in sandstones, but it's not nearly as distinct as what you see in. I'm not sure what it is about the way that the molecular architecture of the carbonate rocks that makes them particularly susceptible to this particular type of shatter coning. I can actually, if people are interested in that, I will quickly pull up a few pictures here of what shatter cones look like.
Yeah. Because we have an astrobleem near where we live, and of course we're on top of an enormous amount of limestone. So.
Okay, let's see. We've got several beautiful examples here. I can see. Oh, look at this. This is okay. Here's a shatter cone from Steinem Basin.
You gotta share it.
Can't.
You gotta share it with us.
Switch your share screen.
Okay.
In that share and start a new one.
Okay, we'll try that again then.
Brad's background is the Recatch structure.
Yeah, good. Okay, here we go.
Ah, wow.
Yeah, they tend to be, and they're called shatter cones because if you get a big enough piece, you'll actually see that the shock wave passing through the stone actually sort of radiates out and produces these cones within the. They got a couple of here. Here's another one. You see the very distinctive. The striations that form within the rock. Now, that's from the shock wave passing through the rock. So shatter cones is another proxy for identifying impact craters.
Yeah.
So if you or impact, let me back up. Impact events.
Events, okay.
Right. Because a crater actually could be in itself probably one of the main diagnostics or proxies. But not always, because there we've got the case of the Recatch structure, which does not appear to be impact produced at this point. Let's see, here's from the Rias impact crater in Germany. It's not quite as distinct, but you can still see the very distinct striations, and you'll notice that they're sort of converging. You see that?
Yes,
they're spreading out.
They look like diagrams of cosmic rays too. That's what it looks like to me.
If would they form like if one of them was an entire piece, would it go all the way around a center, or is it are they pointing at the?
No, it's sort of scale invariant because the whole mass can be like a cone, but then it's cones within the cones.
Mm-hmm. Okay.
In fact, you can almost see that going on here.
Yeah.
In the texture of this particular rock. So these are shatter cones, and you can buy shatter cones online.
Shattercones.com, folks. Get your shatter cones.
Shatter cones right here. Get your shatter cones. Yeah, gosh, what year was that we did the Kentland impact structure, Brad? Well,
that was probably like 2004 or 5. It's been a while.
Yeah, boy, they were just spectacular. We went in and took a tour of the quarry, and there was spectacular, the quarry walls were just exposed spectacular shatter cones. It was very impressive. We would like to get back there, actually.
Yeah, they had that big one at the entrance that was like 3 feet across.
Yeah.
Just sitting outside their office. Sorry, yeah, I was looking for a part for my microphone.
No, okay. No problem.
Okay, Brad. Whatever. Whatever, Brad.
I wanted to show off that thing back there.
So check this out. Now that we know what breccia is, a multi-analytical characterization of silica-rich megabreccias, big broken rocks is what we're talking about, from the proposed natural area of the Recatch Sahara Desert, Mauritania. So whenever you would encounter breccia, of course, the first question would be, what confluence of forces created this breccia? You're looking at broken rock. So in order to break rock, you have to have some kind of a force implied against that rock, right? So obviously an impact of an asteroid or something from space, a large meteor, is going to be sufficient to break rock. But so is volcanism, right? Actually, so is the shear forces caused by a great tsunami coming ashore can rip up rock and throw that rock around. Of course, the more it's transported by water, the less angular it's going to become, right?
Right.
Because a great flood can start out and break up rock, transport that rock, but the farther that rock is being transported, the rounder it's becoming. So at some point, you can find almost spherical rocks that have been, water rolled.
Yeah.
So broken rock with sharp angles suggests that it was not transported
by water
or not far enough to. Right. Impacts, again, the ideal force of nature that you could produce brecciated rock. Or also, you know, a great volcanic explosion, an explosive, like a Plinian eruption, an explosive volcanic eruption could also, you know, blast rock that would then, you know, become breccia. So breccia you could think of as the shattered broken rock itself, but a breccia, but it has more come to be applied to the idea of a subsequent rock that would be considered a conglomeratic rock, where the broken rocks are incorporated into a later generation of lithological generation. So you have the broken rock, then it's submerged or hydrothermally. There are fluids that are percolate through there that eventually fill up the voids between the broken rocks and become a solidified, like a cementitious matrix that now bonds the whole mass together into a conglomerate rock or a brecciated conglomerate, right? So basically the presence of this is telling you that, you know, something happened, whatever it was, right?
Yeah.
So we have mega breccias, so not just ordinary, but mega breccias, meaning there are big pieces of broken rock, which is an interesting clue right from the beginning. So then we also had the resolving the Recatch enigma, which is the doming and hydrothermal karstification above an alkaline complex. Now, what is a karst? Do you know what a karst landscape is? I don't think you have it down where you guys are. Maybe.
We do.
Do you have limestone bedrock?
Yes, and it's karst.
Oh, it is karst.
Yeah, so it's like they call them karst windows or whatever. It's full of hole tunnels.
Full of holes, almost like Swiss cheese in some ways.
I thought you were messing with us. I was like, surely, yeah.
Well, I mean, I was, but
okay, good.
I didn't get it.
My detector is working.
No, I wasn't sure if there was limestone bedrock around where you guys live or not.
Yeah,
but if there is, yeah. So water percolating, you know, carbonate rocks are soluble in acidic water. So if you've got, you know, fractures or conduits through limestone rock and you have water, particularly acidic waters moving through, it will quickly dissolve the rock and produce caves and, you know, conduits and sinkholes and things like that. So here we have doming, and hydrothermal simply means hot water. So there is a limestone layer here. There are several layers. They're old rocks, Proterozoic to Ordovician. So from 1 billion years to about 600 million years, there's these layers of these rocks, sandstone, limestone layers. We'll look at a block diagram in a second. But the idea now is that there was subterranean pressures, like a plutonic event where you had rising magmas, a magma plume coming up under the bedrock cap, which caused the bedrock to dome up like this. Does that make sense? Pressure. Now, one of the possibilities is that has actually been proposed. I have a so like here's an old I don't know if you can see it. I should have actually scanned it in, but this is an old from back 1988, a very interesting article that connects the idea of these large magmatic provinces on Earth, such as the Deccan Traps of India or the Siberian Traps of Siberia or the Columbia Basalt Plateau, as being the result ultimately of great impacts. So the title of this article is Terrestrial Maria, the Origin of Large Basalt Plateaus, Hotspot Tracks, and Spreading Ridges. What he's doing is he's comparing these great basalt areas on Earth to the Maria on the moon. So he says large lava plateaus, which form abruptly within plates without apparent tectonic cause, appear to be the terrestrial equivalents of lunar Maria. Deep erosion of lava plateaus reveals that their magma chambers are gabbro and granophyre complexes. The close association of the Deccan Plateau with the timing of the terminal Cretaceous boundary clay suggests that it is an impact crater large enough to cause pressure relief melting in the asthenosphere. We talked about the asthenosphere in a previous podcast, it's the layer below the lithosphere. It's this boundary zone between the upper mantle and the lithosphere, or basically the crust. And it's a molten area, but it remains solid because of the great pressure. And if you release that pressure, it can convert back to its molten state that it wants to be because of its temperature, its high temperature. So the idea behind this paper is that if you somehow can remove the material that's imposing this pressure on the asthenosphere, it will allow essentially the magma to now upwell. It's now the pressure has been relieved, the magma's upwelling and can spill out and form these basalt provinces like it's referring to here. This was in 1988, so this was before they discovered the Chicxulub impact crater buried under the Yucatan Peninsula, right? So he's speculating that perhaps the basalt plateau, which is the Deccan Traps in India, which was very active right there at the KT boundary, the Cretaceous Tertiary boundary, might have been actually the result of this pressure relief melting caused by the impact. And now that the impact crater would now be not visible from the surface because it's buried under these great sheets of lava, in some cases even a mile or two thick. See, okay. So that's the general idea here. It's an interesting idea. So, but here the problem is when you have an impact, it's going to shatter the rock to a great depth. Right now, clearly, when we look at the Recatch structure, and we'll get to Google Earth here. I think what I'll do is I'll go ahead and on my end we'll go open up Google Earth in a second here. I'm just showing here some of the papers over the years that I had looked at in an attempt to understand this particular structure better, because like I said, I hadn't really looked into it in depth, because at the point that I learned about it, I was studying impact structures, right? So then when the papers started coming out, basically suggesting it was not an impact structure, I kind of moved on. So, but this was the stuff I was referring to. This was actually a thermal research, but this was actually a thesis, a master's thesis. This Guillaume Maton, who did his master's thesis on the Richat Dome, or the Eye of Africa. He referred to it as an isolated Cretaceous alkaline hydrothermal complex. Hydrothermal means that along with the magma's upwelling, there was hot water coming up as well. And so when there's hot water mixed with magmas, it creates a very distinct type of crystallization that can be identified by petrologists. So it's an interesting structure. Let's go to another one here. The Eye of Africa. This is him. This is his. Came out. This is the most recent thing I could really find, which was published in 2014. Again, he's talking about an isolated Cretaceous alkaline hydrothermal complex. Alkaline, of course, means it's made up of certain kinds of basic rocks, for those who have some knowledge of geochemistry. Again, the hydrothermal means that there was water associated with this upwelling of magma. He says here, hydrothermalism played an important role in the evolution of the Recatch complex. It is responsible notably for the karst collapse central mega breccia formation, the alteration sequence of the rhyolites, the potassic alteration of the gabbros, and the stable isotope enrichment of the carbonatites. And I'm sure you guys understood exactly what that was talking about,
yeah,
right?
I totally got it.
So yeah. If you could recapitulate that in layman's terms, Russ.
It's made up of a lot of stuff.
That's it. Yeah, it's made up of a lot of stuff. And that was one of the unique characteristics of this thing, is because there are alkaline basalts and tholeiitic basalts, which are normally not in close association like that. It says coexistence of intrusive alkaline and tholeiitic rocks within the same igneous complex shows the importance of the regional structural system on the caldera history. Pre-existing deep structural weaknesses. Now, this is an interesting line here because it says pre-existing deep structural weaknesses. So this is where I'm not completely eliminating that there may have been an impact event at some time in the early history.
Okay.
because if you see, here's the thing: if an impact strikes the rock, it's going to shatter that rock, right? And it's going to create evidence of this shattering as deep as the crater is wide, generally, right? Or maybe not. Maybe depends on the nature of the rock, the density of the impact, or how fast it's going. But generally, there would be a fair depth of broken, shattered rock in the area of the impact site. Now, because of the fact that it's been broken and shattered, it's going to be easier to remove that rock from the site through various erosional processes over an extended time span. So what it's saying here is that there were pre-existing deep structural weaknesses. Well, I think we could not necessarily throw out completely the idea that those deep-seated structural weaknesses may have originally been the result of an impact.
Okay.
But there has been enough rock removed from overlying rock that the coesite, the shattered rock, the shatter cones that were in the limestone layers there, etc., would be gone. You see, that's the idea. So I'm
caldera.
What?
He's referring to it as a caldera, so he's,
which of course would then imply volcanism as being
right.
the primary agency.
Yes.
Which and clearly volcanism was part of this. The ring dikes that you see, they're composed of the stone called rock type called gabbro, right? We'll get into
maybe a rock hit the volcano.
Well, now the idea in this article that I was referring to here, Terrestrial Maria, the idea there is that these mantle plumes on Earth, he's theorizing, and this is David Alt, J.M. Sears, and D.W. Hindman. David Alt, we know of him because he's with the Department of Geology, University of Montana. So he's done a lot of work. In fact, he's the author of the book, The Humongous Floods, which is a book about the Missoula floods. And in that book, he actually discusses that the Columbia Basalt Plateau, he discusses the idea that it may have been originated through an impact event. And the idea here is that if you've got let's say you've got a cosmic missile coming in and it's moving 20 or 30 miles per second, and it's composed of a really dense material, so it's almost like a bullet, almost like a cast iron bullet, right? If it's coming, and particularly too, if it's coming more or less perpendicular to the crust, now does it have the potential to completely penetrate the crust, right? And that was Alt's idea. And so again, as with the Deccan traps in India, that he's theorizing about in this particular paper, he also theorizes that perhaps under the Columbia Basalt Plateau of Washington and Idaho, there would be basically a buried impact structure. And the original plume, which interestingly now is under Yellowstone, the creation of the Yellowstone hotspot is what created the outpouring, the extrusive outpouring of the basalts that created the Columbia Basalt Plateau of eastern Washington. However, tectonic forces over the last 17 million years have caused that whole part of the plate to migrate through a great arc to the northwest and have offset it, but it left the plume behind. So the plume is down there coming up out of the mantle. The plate over the top of it is moving. So as you have that magmatic hotspot coming up, it's creating all kinds of interesting volcanic consequences for that. So the whole Snake River Plain of southern Idaho is sort of the pathway, the traceway of the motion of the plate over the Yellowstone hotspot. So Alt's idea was that the initiation of the hotspot was originally triggered by an impact and through this pressure relief melting. And I think that's a really interesting idea.
Yeah.
Because that really puts impacts at the very center of terrestrial consequences. You know, others have looked at the connection between impacts, of course, and mass extinctions, but also impacts and fluctuations and reversals of the Earth's magnetic field. And if that correlation turned out to make sense, then yeah, we're beginning to see that impacts is one of the fundamental geological forces determining terrestrial outcomes. So anyways, back to the Recatch structure.
Just for some reference in there, Randall, the video I published yesterday from the Cosmography 101 series, that's the first thing you talk about, Class 19, Segment 2. That's the first thing on that video. So people can go back and check that out and see a couple of the maps that go along with what you're describing.
Okay, where the plates moved over the plume that
right.
we're talking about? Yeah,
right.
Okay, cool.
Okay.
So is that plume possibly being caused by a remnant mass down there of an impactor?
No, probably not. Although if that theory holds up, I mean, the impactor itself, the part that doesn't vaporize in the impact, would probably meld with the target rock.
Okay.
You know, when you have an impact, you know, there's a lot of stuff that happens. You know, for example, tektites is essentially the molten splash that falls back to Earth, right? That's thrown up in the great heat of impact. It's thrown up into the atmosphere and it rains back down, excuse me, on the Earth. And in the process, it can form a whole suite of hydrodynamic shapes, which can be anything from teardrop shaped to spheres to dumbbell shaped to rocket shaped, almost like, yeah. So they can form a lot of different shapes. Just, I suppose, depending on the material, the atmosphere that is falling through, if there's how much vapor is in the atmosphere. I don't know. There are probably a lot of factors that determine what these shapes end up looking like once they've fallen back to Earth. But that was one of the things that was confusing in the early days of tektite research, is because they would do some studies and say, oh, this is terrestrial. And they would look at other studies and say, oh, this is extraterrestrial. Well, the problem is because in that you get terrestrial and extraterrestrial all mixed together,
right,
in varying concentrations. See, so those are tektite, and tektites would be another proxy of an impact event, because the pressure. Generally, I don't think anybody believes that tektites are produced through volcanic events.
Okay,
that would have to be impact, and then vapor basically crystallizes out as you can have microtektites. Like you can have regular tektites that are big enough to hold in your hand. They might be 2 or 3 inches across, right? But then you have microtektites that you can see the same shapes, but they only show up under the microscope. And then a lot of the microtektites are actually microspherules, and these are the little, you know, when the vapor crystallizes out of the atmosphere.
Right, tiny glass beads, basically.
Tiny glass beads. That's exactly right. Yeah. So in this case, let's look at this as this is from the Eye of Africa here. And this is showing, this is a block diagram that shows a cross section. And what you can see here is that there's these multi-rings, which are Gabbro, which is the intrusive equivalent of basalt. So basalt comes out of the ground and spreads out in the atmosphere, right? Gabbro is and that's an extrusive rock. Gabbro is an intrusive rock, but in other words, if the same magma comes up, but it doesn't breach the surface and flow out as basalt, crystallizes underground, that's typically, so Gabbro or Gabbroic rocks are the intrusive equivalent of basalts, right? And that's what you've got here. These are basically
like granite, or is that something else?
Well, granite is an intrusive because granite again is forms, excuse me, under the ground. Like you can have granite, the magmas that form granite can flow out, and of course granites tend to one side of the geochemical spectrum, more towards the silicate rocks, rather than the right, and a lot has to do with the chemical composition of the rocks, what kind of magmas are formed, and of course that is oftentimes how you identify the distinct types of magma, because for example here in these layers you've got, let's see, I might have a better one here. Let's get to this. Okay, so in this cross section of the structure you can see that the dots are sandstones, and then the little block diagram here, these are limestones, and then there's more sandstones, and these are really old rocks. They go back, hundreds of millions of years. But so basically what you've got is you've got this structure, you've got the gray area is the magma welling up from below. You've got these pre-existing, as it said earlier, pre-existing structural weaknesses, which to me, okay, possibly two explanations. One would be that the pressures from below are great enough, and probably through tectonic processes there have been fractures, but it's a fairly flat-lying basin there called the Taudeni Basin that the Recatch structure is found in. And so are the pressures from below enough to cause the fracturing of the bedrock that then allows the extrusion of the magmas? Or conversely, was there an impact that actually was able to cause the fractures? And once you had the cracks within this lid, this rock lid that's holding everything down, it's now free to well up and come out. We'll leave that question for now. The point is that there were weaknesses within the overlying bedrock that allowed this magma to come up and flow out. And we've got different kinds. It's talking about here you can see these little cross sections represent each one of these plumes then becomes a volcano, right? And so you've got, these are basaltic magmas down below. And let's see, we'll go to the next one. And so what you're seeing here is that the magmas have gone through some hydrothermal changes and some chemical changes forming rhyolitic magmas. We're seeing that the overlying structure, as the magma wells out, the overlying structure is falling, essentially dropping down into the magma chamber that is now being voided of the magma. See, so as the pressure below is easing up, it's allowing the rock masses above to essentially subside into the magma chamber. These arrows here show that the hydrothermal fluid, so there was water involved in this, which leaves a very characteristic fingerprint in the type of metamorphism that you see in the rocks. And so as these magmas pass through the overlying rocks, they will pick up the geochemical characteristics of these rocks. And so that is one of the ways that allows petrologists to identify, or volcanologists to identify the source of various rocks, because an event like this in Mauritania is not going to have the same geochemical signature as a similar event in eastern Washington. See, and see, so you've got quartzitic sandstones, and you've got these limestones. The limestones go back, I'm trying to remember, I think they're Ordovician. So I mean, they're old, 600 million years old. So there was a lot of material over this that was removed to expose this thing. And here you can see further collapse of the structure and the beginning of the formation of the rings. And here in the middle, you have this, what they're referring to as the hydrothermal breccia. So you've got this tremendous mass at the very center of this thing. You've got this tremendous mass of brecciated rocks, right? The matrix that they're enclosed in is the cement was formed hydrothermally. So in other words, you're looking at this mass of stuff full of broken rock, all cemented together, and the cement was emplaced by highly mineralized flowing water. And here, if you look at these, like if you look at this, you can see the arrows pointing. This is an offset fault where you're seeing, or a strike slip fault.
Yeah.
Right. You see that moving, and those shear forces are tremendous, and they can cause metamorphism. And so then the overlying rock has now been eroded away, kind of leaving a cross section of what the structure looks like now. Okay. And you can see here as you're looking at it how it's been domed up.
Right.
Been domed.
I was going to say that previous one, it looked like it was ramping down, and now it's a dome structure.
Now it's a dome structure,
because
and you can see
eroded away.
Right, and you can see these layers of rock are dipping or tilting outwards because they've done this. See, forming what are called cuestas.
So the question marks, that's basically saying we don't know how deep the magma chamber is beneath it. Is that
correct?
Okay.
Correct. So if we go back to here, here's a nice colored block diagram kind of showing the same thing. We see the magma chamber underneath. You see the conduits to the surface, how they coincide with the gabbroic rings. So this would have solidified under the surface of the ground.
Okay.
And only later then, when the overlying rock layers are stripped away, are you going to see the underlying ring structure.
Awesome.
It is pretty awesome. Yeah, so what else can I say about this here? There's a fault system, like for example, right here, you see there's a fault and offsetting in the rings.
Yeah.
And that's undoubtedly due to the uplift. And you see, you've got, as it says here, magmatic phases. So you've got the basaltic magma, which is the gray, and then you've got the felsic magma, which is crosses, which is curious because you've got this mixture of these very highly contrasting types of magma associated with each other. External basaltic ring dike is displaced by a north-northeast, south-southwest fault system in the northeastern part of the structure. That's this right here that it's referring to. It's cross-cut by carbonatite dikes in southern and western sectors, which are the oblique crosses.
The slashes up there on the...
Yeah, there they are, yeah.
Okay.
So, and then you've got right here, this is a small volcano sedimentary basin outcrop, which probably at one time held a lake.
Okay.
So I think what I will do is go to this, if we're still screen sharing. So this is a Google 3D relief map. Where you can see the ring structures. Here is a magnetic survey of the Recatch structure, where you see the ring dike, and you see that this ring has been breached here on the southwest. Calling it a Mars system displacement of ring dike by fault. So a Mars system probably held a lake.
Okay.
At one time, and in fact, this whole thing may have at one time held a lake because there are endorheic streams that flow into it, which means that the streams flowing into it basically just dissipate within the structure. And it's along these stream beds that the Acheulean artifacts were found, which, you know, go back to maybe Homo habilis, 100 million to 200, up to about 1 million years ago, maybe up to 1.5 million years ago. From 200,000 back to about 1.5 million years ago, there was stone tools collecting along here.
Like unifacials found along there?
Mostly, what do they call them? Hand axes that are about this. Yeah. That's mostly what they were, because there are chert outcrops in this thing, and chert was a very good, it's a conchoid, fractures conchoidally, so it's very effective for making stone implements and tools. So there were chert outcrops in this structure that were being quarried by somebody hundreds of thousands of years ago.
Wow.
Yeah.
Wow.
So
that's really cool.
This image, well, yeah, here you can see the ring, and this is the mega breccia outcrop at the center, which is right at the center of the structure. And here's an example of a piece of the mega breccia. Yeah. Pretty substantial.
Yeah. God, it's beautiful though. It's just a gorgeous.
Oh, it really is. Yeah. Although this is a false color, it's nonetheless. But there are a lot of interesting little things when you look around. Like, look at this thing up here.
Is that what
ring structure?
Is that what that thing was calling a plug? The magnetic map you had. It was saying there was a plug up there.
No, the plug. Let's see. It's down here. You can see the cliffs are about 600 feet high.
Wow. So if there was enough water, it would be a lake.
Yeah.
Or would it drain out down?
It would drain out this way.
Okay.
And in fact, I'll show you in a minute, it looks like there was evidence for extreme floods over this whole landscape.
Definitely.
look at this. Look at this down here.
Okay, yeah.
Right. So the Acheulean artifacts are found along the stream bed. You can see there's a wadi up here that flows in, forms this ephemeral stream that basically just dissipates. Same thing here. So an endorheic stream is one that doesn't flow to a greater body of water or to the ocean ultimately, or to a river. It just basically disappears.
The water disappears underground. Is that the idea, or it ends
up? It could be that, or it just it's in a dry basin and it eventually just evaporates. The water flows enough to it just evaporates. I mean, you see that happening, for example, in Death Valley, or you see it out in the Mojave Desert. Brad and I have looked at a number of those kinds of streams. And here is when you get up here to the edge of the erosional. Here you see this kind of stuff, which is very interesting. You see what actually looks like recessional cataracts.
Yeah.
So the stripping and exposure of this feature may have involved catastrophism. And tell you what we'll do here is.
What's the scale of the structure itself? Like, how big is this thing? What are we looking at in terms of miles?
Well, let's see. It's generally given as 38 kilometers. So we'll go 38 times 0.62, which makes it about 23 to 24 miles in diameter.
Okay.
So it's pretty good sized.
Pretty big, yeah.
Which is way bigger than the city plan for Atlantis that people are trying to compare it to.
Brad, we'll get to that, Brad.
Well,
Brad.
We'll get to that, okay.
I'm thinking the commenters that I keep seeing that are just bubbling over, try to burst out. When's he going to say it?
Yeah. Well, what's good is I hear what they're saying seems to be like, I want to hear him talk about the Recatch structure. It's not, some of them are like, it's Atlantis, but a lot of them are just like, let's hear what he thinks about the Recatch. So that's true. What they do. Yeah. They're not demanding you say it's Atlantis. Not yet. Maybe after this episode, they will demand that you tell them that this is Atlantis. But so far, they just want to hear what you say.
This is Cosmographia, the Randall Carlson podcast.